Hi everyone. Today we are going to present on learning real-time A-star search planner for unmanned air vehicle target sensing. So my teammates are Sai Prapurna and Pranagit. I'm going to start on the introduction. So autonomous vehicles, which are essentially the mobile robots, they are used in transportation, agriculture, industry, airlines, and in many ways. So autonomous vehicles, vision, decision making, and the control systems, they are all linked together. And the robot planning systems have been a long focus of research. So one of the major challenges that we face for constructing these autonomous vehicles is to find a path that autonomous vehicle should reach its destination without crashing. So for that reason only, path planning is very essential for mobile autonomous vehicles. Path planning should be done considering the aircraft dynamics and movement of the sensor footprints. For path planning, many algorithms are used, but the real-time heuristic search agents make the decisions based on the constraints, look-ahead search, and the heuristic function assessment. So A-star search algorithm is extensively used for the path planning. The main objective of the path planning is to minimize the length between two targets so that the path is in such a way that all the targets are visible when the target reaches its first destination. To address the problems of various targets, the three technical challenges should be added. They are coupling between the path segments, utilization of the sensor footprint, and determining the viewing of the order of targets. Moving on, as I said, the planning path is a crucial thing in this autonomous vehicle target sensing. So standard approach that we follow for planning the path is to plan the segments that are optimal from one point to another point. To plan the segments for multiple targets, the approach involves planning an optimal path from starting point to the first target, from first target to the second target, and so on until the final destination target is reached. If the targets are widely spaced, relative to the turning capabilities of vehicles, the above approach where we start from the first target and move on to the until last target is followed. And by using that approach, the optimal visit order can be specified. But if the targets are closely spaced, the coupling between the path segments due to the dynamic limitations of the vehicles can result in a poor outcome. So in the next slide, we'll see what is the negative effect of the coupling if the targets are closely spaced. So if you see here the figure, in figure 2A, there are three targets, and the optimal path if the heading of the vehicle, once it reaches the target A, it is in such a position that the target 2 is not visible to the first target, which makes it difficult to reach the target 2 and identify the path that is needed for it. But if you compare figure 2, after completing the segment, after reaching the target 1, it is in such a position that target 2 is clearly visible to target 1, and it is leading to the minimal path that is needed for the vehicle motion. So most planning approaches produce paths directly over targets of interest. So we have download looking sensors, which are like LiDAR and ED video. So it utilizes the UAV sensors. So viewing a target typically doesn't require flying on the top of it. So directly flying over the targets imposed by these planners do not utilize this range and flexibility provided by the sensory input. So how we utilize the sensors when viewing the closely spaced target. One of the major challenges when viewing the closely spaced target is to determine its viewing order. Added complexities for this closely spaced target is its turn radius and sensor footprint. So considering this complexities, we are going only to consider the constant altitude, constant velocity, and the downward looking sensor. In addition to this, viewing this order of the path planning problems are considered to have added complexities to find the turn radius and also the sensor footprint to exploit. Moving on, this path planner plans an optimum and near optimal path through the multiple targets by overcoming the effects of the coupling between the path segments. So this path planner, it utilizes the sensor footprint to view the targets, thus eliminating the need to fly directly over them. Path planner, it requires only a list of targets as input and automatically provides the order and times in which the target should be visited. Determining the viewing order of the targets will yield the minimal length that is needed for the vehicle to motion across the targets until it reaches the final destination. So according to the simulation data, MEA stars performs better with more computational efficiency when compared to this path planning algorithm. So it takes less time to develop the shorter paths and it uses a less memory. Furthermore, the proposed system outcomes the traditional grid-based planners is congested routes and complex conditions. Because of these advantages, the mobile robots with the limited memory and energy can be employed to the proposed research. Discrete step paths. So the successful path planning algorithm should be in such a way that the path that is defined, it should utilize the full capacity of the vehicle sensor, and also it should satisfy the vehicle dynamic constraints. The above capabilities, which are the vehicle sensors and also the dynamic constraints, it can be provided by the discrete step paths, which are built by assembling the primitive turn and the straight segments to form a flyable path. The specific length of each segment is a ds, and the length of the segment can be a straight line or a turn. So by normalizing this primitive segment length with the minimum turning radius, it gives the vehicle the maximum heading change that is needed at each step. So the good strategy to organize all these calculations is to establish a path that isn't restricted by the endpoints or the directions, and it should use the full capability of the vehicle sensors, and that should meet the vehicle powerful needs such as the dynamic constraints. So assembling the left turn, right turn, and the straight primitive creates the flyable paths. The right path tree, it has a depth of 3, and the nodes in the path tree have a parent node A, and it has a set of child nodes C. Each node has a record of target, and it has been sensed by its ancestors, which is denoted by a set F. So it's quite evident that shorter step length increases the resolution of the path tree, whereas a greater length path increases the coverage area of the tree. If number of nodes in the tree goes exponentially with the depth of the tree, there is a practical limitation that the tree depth is imposed by the computer memory limits. For the desktop computers, which are used currently, the tree depth of 30 to 50 can be implemented feasibly. Here we can see the notation for the path planning problems and also the geometry of the nodes of the path tree. So the configuration of the vehicle at node A is given by P equal to X, Y, and lambda, where X and Y represents the inertial position, and the lambda is the heading of the vehicle that is measured towards the north. So the vector of the vehicle is the ith, which is denoted by d of I. And the configuration of the child node is determined by calculating the change in the heading and position relative to the parent configuration. Discrete steps paths are implemented and are limited to the 2 dimensions to reduce the computational complexity. However, if you want to build the discrete step paths for the 3 dimensions, it can be extended using a straightforward manner. Moving on, my teammate Sai Prapurna will continue on discussing about the LRTA start research. Thank you.
Today we're going to discuss about the LRTA research in the first topic, and this applies upon the learning real-time methods algorithm, and this is accomplished with desired path planning objectives. The LRTA algorithm is established especially for typically applied to path planning problems in grid-based worlds. And for LRTA algorithm, it may be applied to a type of world that is grid tree and direct path, and other are chosen, and it is chosen because of the faster star algorithm compared to that, and because of the limiting factor of the performance of the path, and the execution speed is reduced, and the spatially complexity of the search. And heuristic search, also known as the informed search, selects the next state and to expand based on the specific information about the issue. Constant inquiry tacks are the quest is ended once on the S goal is located. The method updates this estimation of the distance between the current state as current and the objective at each iteration, giving extra information about the environment. And a short amount of time while sensing just a small percentage of the climate is a specialist current location, and it continuously heuristic inquiry chooses tasks based on the limited look, ahead search, and the heuristic. And the next slide. Terminating conditions are the first. In the first picture, we can see the distance to the furthest remaining objective, and in the second picture, we can see the distance to the nearest object plus distance between nearest and furthest. It is a calculation between the initial object and to the final object. It is a here we can see the target 1 and target 2 and target 3, but from the target 1 and target 3, this is a final destination. From initial point to target 1 is initial point and target 3 is destination. So the current point we're eliminating the target 1, taking the point 1 to the target 3. That's the calculation of initial heuristics. The next slide is branch terminals. To get the best results from the LRTA tree search, memory management and path tree trimming are required. The current node is terminated by its removing its children and setting its heuristic value to the infinity. When the heuristic value of node is always less than or equals to the actual path length. If all the nodes of one's children have heuristic values of the infinity, the node is dead and can be terminated in the same way. That's the branch terminals. And here you can see the diagrams. Okay, it is a path tree search, path tree size, and the size of tree grows very quickly as a step decreases, and it takes time to consuming. It takes time to explore the tree, and the whole path tree is 3D in size, and these DR levels. This is level 1, level 2, level 3, level 4, and level 5. This is the root, and this is the C. Okay. Even through search with no need to visit all the nodes, there is a huge number must be examined, making the search lengthy and inquiry large number from this page to the whole and the nodes visited. The next one is the testing and the comparison. In the testing and comparison mentioned in this paper are LRTA tree search validation and path length and running times, different number of targets. As we have seen in the previous slides, there are different number of targets like target 1 to target 3, where the initial point and the final point is taken. We have to reach the initial and the final destination in a shortest way. And the NLRTA algorithm terminating conditions are less than 1 minute, and data from each terminated runs was used in this research. And this NLRTA algorithm terminating condition was 10,000 times less than this, and the step size used for the discrete step path tree has a direct influence on the running time and the path length performance of LRTA research algorithms. It can show in the image, and increasing the step size significantly reduces the algorithm's running time. And the running times are the results of the path length and the running time test shows the rising and the step size increases running time without affecting the path length performance. The test results also reveals that the NLTA tree method is faster than the LRTA algorithm and performs similarly in terms of path length. And running times for calculations are it depends upon the quantity of hubs visited by the hunt to give running time information in a stage-free way. And the next two slides will continue by Patchmate. Go, Pranay.
Yes, the next paper is we can talk about is Canon LRT extra search. It is a simple subgoaling for real-time search. Basically, this LRT extra search is mainly used in video games where the real-time requirement is seriously necessary here. The distinguished feature of the real-time operation is that the agent must plan and execute the actions repeatedly within the fixed time limit. It is basically used for pathfinding in real-time situations. Their commitment time will surely increase as the problem grows in size and surpassing any definite predefined limit. In real time, such approaches, the issue is in fundamentally different manner. Real time search algorithms measures only a few initial actions for the agent to take rather than to complete possibly abstract the solutions before the first activity is to be considered. This LRT star search is typically accomplished by conducting a fixed depth look ahead search around the agent's current state and employing a heuristic search to select the next few actions. The actions are then carried out and the planning execution cycle is repeated. Because most such local searches do not reach the goal state, and the agent runs the risk of reaching a dead end or more broadly selecting a suboptimal actions. The first real-time heuristic search algorithm to produce this was DLRTA search. Here D refers to dynamic LRTA search. The DLRTA star search examines a state space and creates a database of subgoals that are then used for runtime during the pre-processing phase. As a result, even with the myopic look ahead of one, it outperforms the previous algorithms significantly. Yeah, we can move on to the next slide. Here we can see the subgoal database construction. Here the DLRTA star takes into account all pairs of abstract states. Here we can see in the diagram about the abstract states. The subgoal as defined by the LRTA search as agent, as state, and as goal. The market state is saved as the subgoal for the abstract state pair, as we can see in the figure. The memory requirements are O of V plus V2, where V represents the number of ground level states and V represents the number of abstract states at the abstraction level. This DLRT star code is non-trivial because it requires the construction of the click abstraction, the identification of ground level representation, and the execution. Besides that, since multi-level abstraction is commonly used in practice, the code must be written for general graphs rather than the rectangular. Then we set out to create a more user-friendly method of creating a subgoals database. As an outcome, our strategy is based on the following concept. LRT star search, the look ahead of one is the simplest and fastest version of the real-time search algorithm. A myopic LRT star is essentially a simple hill climbing heuristic enhanced with a Bellman update rule. Then we would more prefer we'd basically prefer that our LRT search not learn most of the time in order to avoid any learning and problems that it can cause. In the next slide, we can see some examples where we can set the basic state goal and state start goal and start receivers. This is achieved by choosing a sub goal that is close enough to the agent to be reached, but simple hill climbing. According to the situation, a subgoal is defined as follows. Given a current state as start and goal state as goal. Best subgoal is the farthest state along the optimal path from as the start and the ending point. It is reachable from a start via the previously discussed simple hill climbing technique. The result algorithm is of line data building component of the KNN LRT research. We begin with a map and the described number of subgoals n. We then generate n random pairs of ground level states, and both are reachable at the two moves apart. Next slide, we can see that runtime search. This is basically we use runtime search for non-trivial maps. There are most of the time the agent state and the goal state will not be found in the database of subgoals. The comparison is described as a sum of heuristic distances between the start and the end goals, as well as between the start goal and end goal. On maps, the heuristic distance is usually a particularly specified function as an Euclidean distance. All of these distances does not account the map substitution. When an agent typically finds the database record that is most similar to its current situation, it sets the subgoal as subgoal from the code you can see. from that record as it has its own subgoal and proceeds towards its using the standard LRTA method. As we can see some properties here. At any given point of time, LRTA either executes the LRTA search or it can compute the subgoal. The former meets the limit of real time. This is because the database N is independent of the map size. The hill climbing checks are limited by that. If the map is finite, and the goal is the same connected component as the initial state of the goal. Suppose in a worst case scenario, the agent will stop computing correlation and determining hill climbing reachability for all the records in the database. Now, next slide, you can see empirical evaluation. In this paper, for empirical evaluation, there are 8 tabs that are considered from the most popular video games. Like Warcraft and all. The maps are ranging between 150 cross 141 to 234 cross 274 grid cells. 128 different pathfinding problem instances are created for this testing purpose. Despite being constrained in such a way that the optimal solution cost for the paths were similar, specifically in the range from 100 to 150 meters usually. Each data point presented here represents an average of 1024 different pathfinding searches. The suboptimality as a function of database size is depicted on the left subplot, as you can see in the right. The database size is reported in relation to the map size. It is worth noting that LRTA star subgoal databases are generally much smaller than their dynamic LRTA search counterparts. To conclude the topic, we can say that the LRTA algorithm is guaranteed to produce a minimum length path, but with longer times. The main motivation for this search was to create a new high-performance real-time search. Both LRTA star and NLRTA star algorithms provide viable solutions to these multiple closely spaced target spacing problems along with flexibility. The new algorithm Canon LRTA star provides clear advantages for pathfinding applications in video games. Not only is its database computation similar to implementation than that of dynamic LRTA star, but it also provides nearly as good runtime real-time performance while requiring significantly less memory to store the subgoal database. These are some of the references that we took data from. Thank you.